Welcome to the Walton Pie. So today we're going to talk about something that was casually mentioned to me the other day, and I thought it would make a really good video. So it was mentioned that this sum probably has a formula, but the person I was talking with didn't know what the formula was. So I also don't know what the formula for this is, but I figured this would be a good opportunity to show the process that we can go through and that mathematicians often go through in trying to come up with these different formulas and theorems that we see, and try and go through the process of how would I do this if I was trying to solve this sort of problem. Because most of mathematics is not memorizing formulas, but recognizing a pattern and then trying to show that that pattern has to always be true. So let's try and figure out what on earth a formula for this is, and then see if we can prove that that formula is actually going to be true all the time. So the way that I would do this is I would just write down the first several values for different values of n to see what this is going to be. So let's start to do that. So let's see what we got. So we got different values of n, and then let's see what the sum, oh that's a very thick blue, let's make that a bit thinner. Okay, and then let's look to see what's the sum as I goes from 1 to n of I to the fifth is. So we're going to make a little table and see if we can figure out what the pattern is. So when n is 1, that's just going to be 1 to the fifth, so that's 1. When n is 2, that's 1 plus 2 to the fifth, so that's 33. 3, that's 1 plus 2 to the fifth plus 3 to the fifth, and that is 276. 4, 1 plus 2 to the fifth plus 3 to the fifth plus 4 to the fifth, that is 1300. Continuing this pattern on, we can find that 5 is going to be 4,425. And let's do 6 while we're at it. And we'll see that 6 is 12201. So once we have these different things, we're going to try and find a pattern in this. Now, just finding a pattern in these terms themselves, so 1, 33, 276, 1300, 4425, 12,201, just looking at them this way, that's probably not going to be very helpful. So the next thing I would look at is I would look to see what are these when they are factored, and see if I can find a pattern in the factors. Well, 1, that's just 33, well that's 3 times 11. 276, if we go through and figure that out, that becomes 2 cubed times 3 times 23. 1300, a little bit easier, that's 2 squared times 5 squared. That gives us 100, and then times 13. We got 4425, that's a 3 times 5 squared times 59. And then we got a 3 times 7 squared times 83. Now, at this point, we're going to try and see what patterns, if any, we can spot. Well, one pattern that I'm seeing is we have these really big numbers that come up at the end of our factoring, and for the most part, they're going up each time. 11, 23, 13, that was a little odd, but then it goes to 59, 83. So there's probably something involved in that pattern. So let's try and figure out if we can identify what that pattern is. So let's get a little bit of space. So we got a pattern that we recognized. So it went 1, 11, well actually we don't know if it's necessarily 1. So 1, we don't know what that term would be in that pattern, but it would go 11, 23, something, 59, 83. Let's see if we can figure out what the pattern might be here. So one thing that we might have is maybe they are some sort of like doubling pattern, because 11 and 23, those are about multiplying by 2. So maybe this is a times 2 plus 1. But then to go from 59 to 83, that's not going to work out very nicely with a multiplication plus something. So it probably isn't that. So if it's not multiplication, maybe it's a plus something. So that goes a plus 12. From 59 to 83, that's a plus 24. So it's not adding the same thing every time, but maybe we can figure out what it is adding each time. So we know that we're going to have two jumps to go from 23 to 59, but that the total distance between them, that is a plus 36. So the average might be a plus 18 plus 18, but that doesn't really fit a pattern. 12, 18, 18, 24. Like, yes, 12 to 18, that's a plus 6 in the difference, but then it's 0 and then it's a 6 again, so it's probably not that. But if we modify it a little bit to say, what if it's 12, 16, 20? 16 and 20, that adds to 36. So that means that the next one, to go from 83 to the next thing, we should probably add 28. And if we add 28 to that, well, 83 plus 28, that's 111. So if we were to do the next term, hopefully there's a 111 that comes out. The challenge, though, is 111 isn't prime. So we're going to have to figure out what the factors of that are. But 111 is equal to 3 times 37. And we should also probably check to see if this number in the middle showed up as well. Well, the number in the middle, 23 plus 16, that gives us a 39. So that should be a 13 times 3. We have the 13 but not the 3. So that means there's probably some division involved in this as well, if this is the right pattern. We don't even know if this is the right pattern yet. But let's go through and see what happens if we look at the next term in the sequence. Well, 7, that goes to 29008, which is 2 to the 4th times 7 squared times 37. So we got the 37 that we were wanting, but we didn't get the 3. So that means we're probably going to need to include some way to represent this pattern, and there's going to be a division by 3. Now the question is, how do we write that pattern? How do we write this pattern where it goes plus 12, plus 16, plus 20, plus 24, plus 28? How do we write that? Well, it's similar to the pattern where we go plus 1, plus 2, plus 3, and this formula, well, that's just the sum of I, from I equals 1 to n, which we have a formula for, which is n plus 1 divided by 2. But we are increasing each term that we're adding by 4 each time, which means we are going to need to be multiplying this by a 4. So we are going to have a 4 n plus 1 divided by 2, which all simplifies down to 2n plus 1. But the challenge then is we also need a over 3 sort of thing, just to be able to compensate for all of those different pieces that we're dealing with. So what we'll have is we will have this over 3, and now we just have to figure out what do I have to shift that by to be able to get to the correct piece that we're dealing with. Well, if we were to just look at that one piece of the pattern, let's see what that would give us. So let's see, let's zoom out a bit. Let's give ourselves a bit more room. All of that. Let's shift that over. Okay, so we got our new pattern that we are going to be dealing with. So we got 2n times n plus 1 over 3. Well, let's see what that is going to give us for these different values. So 2 times 1 times 2 over 3. Let's see, that goes to a 4/3. Let's see, 2 times 2 times 3 over 3, that goes to a 4. Let's see, we got, wait, no, that doesn't go to 4. Let's see, so that's, okay, let's undo that. Let's be a bit more careful with this. So we got 2 times 1 times 2 over 3, so that's going to be a 4/3. We got a 2 times 2 times 3 over 3, so that is going to be a 4. Let's see, we got a 2 times 3 times 4 over 3, that gives us 8. Okay, so these aren't working out quite as we were hoping, but let's try and see if we can be able to pull those different pieces in. So we need to adjust these somehow. Let's see if we can figure out how we need to adjust them. So let's see. Well, let's ignore the dividing by 3 piece for the moment. So let's get rid of that part, and then we'll deal with the rest of that to see how close we are getting with those. So let's forget the dividing by 3, and if we just do the 2n times n plus 1, that'll be 2 times 1 times 2, so that'll be a 4. Let's see, 2 times 2 times 3, that's 12. 2 times 3 times 4, that's going to be a 24. 2 times 4 times 5, that is 40. 2 times 5 times 6, that's 60. And here we're starting to see a little pattern. If we go at 6, that'll give us 84. This one gives us 112. Notice each of these, or at least the ones that are underlined in red, are just one bigger than it. So that means we are going to need to also have a minus 1, at least to get our pattern to match up. So when we do the minus 1, that'll change all of these. Let's see, let's fix these real quick. So that is now 3, 11, 23, 39, 59, 83, 111. Now the problem is we also had a dividing by 3 that we had to deal with in a couple spots. Because the 13 goes into the 39, but we're missing a 3. So we need to have a divided by 3 in this to be able to compensate for that. So all of these are going to be over 3's. And now we are going to figure out what's left in the pattern. So if we are going to rewrite this, let's do it where we drop this one term. This term shows up, at least we think it does, in the ones we've looked at. So we think that piece is going to stick around. So let's drop that one and look at what happens when we factor out that much. So if we look at n, we have the sum of I to the 5th, where we drop the 2n, n plus 1, minus 1 over 3 part. And we're going to look to see what are the factors there and see if we can find a pattern there. So we get n is 1, 2, 3, 4, 5, 6, and 7. So we have all of those. And when we drop the pattern, once we've dropped that piece, we are left with a 1/3, 3, 2 squared times 3. Oh, whoops, I forgot the over 3 part. Sorry. So we have 1, we have 3 squared, we have 2 squared times 3 squared, we have 2 squared times 5 squared, we got 3 squared times 5 squared, we got 3 squared times 7 squared, and we have 2 to the 4th times 7 squared. And these are just going through and taking these factored things, including an extra 3 everywhere, and then we are going to be able to then drop the 2n, n plus 1 minus 1 piece. So we've gotten that much, and so now we're going to have to figure out, is there any pattern in this that we can be able to spot? So one pattern that I'm seeing is that we have 7 squared and 7 squared, we have 5 squared and 5 squared, and then we have 3 squared and 3 squared. And then we also are having these pieces that are showing up. We have 2 squared, 2 squared, 3 squared, 3 squared, and then we have a 2 to the 4th, so my guess is the next one will also have a 2 to the 4th. And if I was to hazard a guess, I'd say it would be a 2 to the 4th and a 9 squared. Because it looks like going each of these spots here is going 3 squared, 5 squared, 7 squared. But then why does it go 2 squared, 3 squared, 2 to the 4th? Why does it go back to 2 and increase the exponent? Well, what's another way to write 2 to the 4th? 2 to the 4th is the same thing as 4 squared. So it goes 2 squared, 3 squared, 4 squared. That is a really cool pattern. So we got 2 squared, 3 squared, 4 squared, probably 5 squared next, at least our guess. And then we have 3 squared, 5 squared, 7 squared, 9 squared, 11 squared, and so on. So if we were to make that our guess, how would we write that? Well, the exponents on this side, these are going up by 2, but then on this side they're going up by 1. Ideally, we'd like them to be going up by the same amount so that we can be able to write them in a simple pattern. So what happens if we were to just make them like all go up by 2? So one way to do that would be to double each of these terms that we're raising to a power. So if we were to do that, then we'd have, this would be 4 squared, 6 squared, 8 squared, 10 squared, which would then allow us to be going up by 2 each time. But the challenge with that is, what did we change? Well, to go from 5 squared to 10 squared, so 25 to 100, that's multiplying by 4. 4 squared to 8 squared, 16 to 64, that's also multiplying by 4. So what we're doing is, by rewriting them like this, we are introducing a multiplication by 4, so to compensate, we're going to have to divide by a 4. So that means the other piece that we're missing is going to be something over 4. So now how do we write this pattern where we know that we have an over 4 on it? So let's go through and look to see what that would be. So we got 1, 2, 3, 4, 5, we got n, and then let's write down these patterns. So 2, that should be a, oh, remember we have to multiply everything by 4. So that means this is going to be a 2 squared times 3 squared. Then we got a 4 squared times 3 squared, 4 squared times 5 squared, 6 squared times 5 squared. 6 was a 6 squared times 7 squared, and then the 1 was a 2 squared times 1. How do we write these? These are the different patterns that we have left over. Well, these different patterns, remember, they're always just one bigger than each other. So it goes 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7. So that means we probably have an n squared, because whenever we have 3, that's 3 squared. 4 is 4 squared. 5 has a 5 squared. 6 has a 6 squared. Each of these have something in them, and the other term that's there is the n plus 1 squared. So that means our other term is this piece plus the dividing by 4. So our guess is the other piece is n squared, n plus 1 squared divided by 4. So that means that our guess for the pattern is that the sum from I equals 1 to n of I to the 5th is equal to this pattern, n squared, n plus 1 squared over 4, times our other pattern, which was 2n, here let's rewrite that one, so we got 2n, n plus 1 minus 1 over 3. So that is our pattern, which, if we rewrite it a little bit, would give us n squared, n plus 1 squared, times 2n squared plus 2n minus 1, all over 12. And so that is our guess for what the pattern is. Now the question is, can we prove it? Can we prove that this is always going to be the case? So, how would we prove this? Well, let's go through and do that now. So we want to prove that the sum from I equals 1 to n of I to the 5th equals n squared, n plus 1 squared, 2n squared plus 2n minus 1, all over 12. How would we approach this as a proof? Well, the way we're going to do it is going to be a proof by induction. So, first thing we need, base case. So our base case, this is n equals 1, sum of from I equals 1 to 1 of I to the 5th, that's equal to 1. that is equal to 1 times 2 times 2 plus 2 minus 1 divided by 12. Oh, that's a 2 squared. So we got, this is 4 times 3 over 12. Okay, so our base case is done. The next thing is we need our inductive hypothesis. So inductive hypothesis, basically what this means is we are going to assume that is true when n is equal to k. So the sum I equals 1 to k of I to the fifth is equal to k squared, k plus 1 squared, 2k squared plus 2k minus 1 divided by 12. And now for our inductive step. Inductive step is where the bulk of this work is going to be. So in our inductive step, we're going to look at the sum from I equals 1 to k plus 1 of I to the fifth. Well, that's going to be k plus 1 to the fifth plus the sum from I equals 1 to k of I to the fifth. And then here's where we use our inductive step. This is equal to a k plus 1 to the fifth plus k squared, k plus 1 squared, 2k squared plus 2k minus 1 all over 12. And to get everything to be able to combine as a fraction, let's rewrite this one as this being multiplied by 12 over 12. So we got a 12 over 12. So there we go. So that's us using our inductive step. Now our work from here is to turn all of this into this, but in the form where all of those k's are replaced with k plus 1s. So let's get on with it. How would we approach this? Well, our goal is to end up with a k plus 1 squared times k plus 2 squared times a bunch of stuff. So that means we're going to want to keep k plus 1 squared from everything. Well, fortunately we have some k plus 1s that we can keep around, so let's go through and do that. So this is going to be equal to a plus 1 squared times whatever's left. And everything's over 12, so let's pull that over 12 out. So we are left with a 12 k plus cubed plus k squared times 2 squared plus 2k minus 1. And now let's expand all that out. So we got k plus 1 squared over 12 times, we got a 12k cubed plus 36k squared plus 36k plus 12. And then let's see, we got a plus 2k to the fourth. Let's see, plus 2k cubed minus k squared. So let's see, let's combine some terms. We got k plus 1 squared over 12 times, we got 2k to the fourth. Let's see, we got plus 14k cubed. Let's see, plus 35k squared. Plus 36k. Plus 12. Okay. At this point we might be like, great, how on earth am I supposed to factor this? This is a quartic. I really don't want to try and factor that. I don't want to look up the quartic formula. It exists. It's a mess. I don't want to look it up. How can I do this? Well, remember, we are hoping that we can get a k plus 2 squared. So that means if we can divide this by k plus 2 squared, which is k squared plus 4k plus 4, if we can divide that all the way through, then that means we have some hope. So let's go through, and if we divide that all the way through, it turns out that it does factor. So we get, and you could do this by doing polynomial division or something. So you get a k plus 2 squared, and what we are left with is going to be 2k squared plus 6k plus 5. Okay, there was a slight mistake. It's not plus 5, it is plus 3. Okay, so now that we've got that, now we just have to factor this bit. Well, our hope is that we can get this to be in terms of k plus 1s. So let's see, so we got a k plus 1 squared, k plus 2 squared over 12. And we want to rewrite that in terms of k plus 1s. Well, that's going to be a 2 times k plus 1 squared. Now let's see what this is. So that's a 2k squared plus 4k plus 2. So that means that took care of 4 of these k's, which means we have 2 k's left. So we have a plus 2, and we want that to be a k plus 1. So that's a plus 2k plus 2. So that means we have a plus 4. We need a plus 3, so we need a minus 1 at the end. Whoops, let's put that as purple. Minus 1, which is precisely what we wanted. Which means, therefore, the sum from I equals 1 to n of I to the 5th is equal to n squared, n plus 1 squared, 2n squared plus 2n minus 1 all over 12. And we have successfully been able to prove this one identity. Was it easy? Not always, but what we were able to do was we were able to go through and find these patterns, be able to identify these patterns, pull them out, and once we identified those patterns, all that was left was to try and show that this pattern will work all the time. And we successfully were able to do that. And this is what we can do in all sorts of different situations. Most of these weird formulas that we see are people saying, well, here's an interesting pattern that I spotted. Can I show that this is always true? And some of these patterns, I am absolutely bewildered that people were able to spot them. Like the prime number theorem, that one, I am honestly impressed that anyone was able to spot that pattern, because it's this really weird pattern that, look it up if you'd like, but it's just amazing that people are able to spot these patterns and be able to show it. And hopefully this video helps you be able to see, how can I spot these patterns and how can I show these things and come up with these ideas on my own, so that you can be able to also be able to be doing mathematics. Because honestly, this is what mathematics is, and this is why I find it so beautiful. It's finding these patterns and going through and trying to do them on our own, to be able to show that these patterns are also going to be eternal and that they last forever. Anyway, I hope you enjoyed this video. If you enjoyed it, please like and subscribe. It really helps me to be able to make a lot of these videos, and I hope you all have a good rest of your day and good luck with all of your math.